So you read an article for today, and sample overload, not about the coatings, not about the columns. That's coming up. Okay, so when you see these images like this, these black and white kind of images, what kind of images are these? Yeah, what type of microscope? Electron microscopes, STM images, right? What's STM stand for?
Somebody that was in micro.
Scanning, tunneling, microscopy, right? The electron has to do energetically impossible things for this to work, right? You can see the resolution on here, 3 times 10 to the negative 6 meters, right? 20 times 10 to the negative 6 meters. They blew it out a little bit, okay? So this is what their stationary phase looks like for what type of chromatography? Because now we're not talking about all types of chromatography anymore. Now we're kind of falling into one type here. It's liquid. It's liquid chromatography, right? So what they have is, I'm not sure what type of chemical that is, but inside I know it was a little tiny glass sphere. So engineering-wise, we're really good at making little tiny glass spheres, I guess, right? We can really control their size really, really well. Okay. So what do? They coat it with compounds, and organosilanes is what they do. Because what's glass made up of? Sand, which is what? Silicon and oxygen, right? SiO2, right? And now I'm sure there's some impurities and stuff, but that's essentially what it is. But if you have the silicon oxygen crystalline lattice, what's on the surfaces? Right? Because you're going to have a bunch of oxygens, right? Anything else? Right? You end up having, I should have Googled the lattice of, I forgot my little line, see? Right? Just start drawing all this stuff. Draw it out. Google it, could look a lot better. But the point is, on the surface of this stuff, you don't just have oxygens, you have OHs. All right? I should draw my little line down here further. You have OH groups sticking out all over the place. So that would mean that glass is what type of compound? Sounds odd, but is it polar or nonpolar? Or is it very organic? How would you describe the surface of glass? Very, very, very polar, right? Because think of water. Isn't water supposed to be thought of as a polar compound, right? So this is on the extreme end. Glass. So if you take a hunk of glass, right? Now I got to turn the lights for this. Why not do what they did? Instead of coating a little glass sphere, let's coat a hunk of glass. Okay? So this is an uncoated piece of glass with octadecal silane. What is octadecal? Octadecal.
Is it 18 or 18?
It's 18. 8 in the 10. 18. So what you have is you're going to have that silicon, oxygen, and then C, right, well, I guess CH2, CH2, CH2 with a C what on the end? CH3, right? 18 carbons. Okay? But that is this piece of glass. So let's take a look at what water would look like on these two hunks of glass here. So this is the uncoated one. If I put a droplet of water on it, all right, or several, yeah.
That's uncoated?
This is uncoated. Just pass it around. Try not to lose my drops. Okay.
Yep, they look like drops.
So it looks like drops. So one thing that this whole idea of coating glass and organosilane has been around for a while. But the applications, people, it takes a lot for people to think about stuff. There's not too many Galileos around anymore, right? So how about making mirrors coated with this stuff, right? Because if you have a mirror's just glass, right? Silver on the end, reflective on the other side. What would happen if you had it coated with octadecyl silane, something very, very organic? You could use this mirror where? In the rain, showering, everywhere, right? Coated on in your automobile, right? The windshield, never fog up. Realize this stuff is actually, you can take your scraper to it and everything, because this is part of the glass. That's a covalent bond here. Once you get rid of that H and have your octadecyl on there, right? So this is tough stuff. Cost of doing that? We just did it, right? So see, I can rub it. I don't need to be super lens. Well, I should probably, right, to keep scratches and things, but I don't need any super strong lens paper or anything. I can just rub it, and then you put a drop on here. Now it's going to be the difference between the two drops. This is water. I'm going to drop it on octadecyl silane coated glass. And what's going to be the difference between the two drops? What's going to happen? Adriana, what's going to happen? What's going to be the difference between the drops? Should there be a difference between the drops? In this uncoated glass, OH groups, polar surface. C18 coated glass, very organic. Water loving or water hating? Hating.
I thought it was gonna
It should be water. Shouldn't it be water hating? Because it's organic. It's like oil on there.
Yeah, I see. Yeah,
right?
That chain of carbons.
Yeah, that big long chain of carbons. So that's the thinking of you making mirrors and windows and all that stuff with this, because it'll just repel the water, right? Let's see here. All right. Then look at he's just beat it up. Now he'd get beat it up even more if we knew what we were doing when we made it, because I'm sure he's not coated as well as he could be. In other words, there's probably a lot of exposed what on that glass still? OH groups, right? So he's not as repellent as he could be if we were really good at what we were doing. We're just playing around in the lab, okay? So, but that's the problem also with chromatography that we're going to see in a little bit, that it's hard to cover all those OH groups. Well, can you see it? Now, what's the technical word for that? Does anybody know? They call it the contact angle. It's a huge contact angle that is just repelling the water. You have to really zoom up with a microscope or whatever and take a photograph and measure the angle. Okay, but it's really repelling the water in comparison to the first hunk of glass we passed around. Okay, so someone else turned in their, for the very first class period, it was a quiz very first class period was a quiz on just turning in the terms. So and I accepted someone else's late, so you can turn yours in too.
Right now?
No, whenever you have a chance.
Oh, because I stapled the terms to the...
No, for the very first class period.
Oh, I already...
Oh, okay. Okay. Yeah. Partition chromatography. The most common type of liquid chromatography performed today. It's bonded phase. That's what we're talking about. In this type of chromatography, the stationary phase is chemically bonded to a what? A little glass bead. Yep. Little glass bead. So right there is going to be a uniform size, because all those glass beads are all 2 micrometers or whatever in size. Like, see? Here they're all 3. Okay. So what does it look like? Well, so we're supposed to have, you could say uncoated. you'd have a bunch of what groups sticking out here? All everywhere. OH groups. Okay. And then they have some proprietary process, right, or patent, easier to spell, right? They're not going to say, everyone's got their own ways of doing it. Now, there's some published articles. That's how we got ours done. Okay. So all those little 1, 2. Let's not do octadecal. Let's do C8. Right? I have to put so many carbons on there. Octyl silane. 1, 2, 3, 4, 5, 6, 7, 8. Right? I guess you should have H's on here. It's going to be a lot of drawing. So we'll draw one of these right, and the rest I'll be lazy on.
You can do some skeletals.
Yeah.
That's what I did.
That'd make more sense. All right, so then you'd have a bunch of them, right?
Pretty good.
Okay, but some of them are not coded. So leave some blank.
They said 8.
I know.
Yeah, well, you could do 18, but then look at all the C's you'd have to do. So we're code. We're have.
No, H and so unprofessional. Whoever did this.
Okay. Where are we? Oh, I don't have the question there. I'm going to have to add it. Okay. So we're supposed to get, the goal is to get pretty peaks, right? If you have a chromatogram, what are the axes? What's the X and the Y axis? Detector signal and what was the other one? Time, yeah. Detector signal and time. Okay. Let's zoom in, and you want a nice pretty peak, right? Symmetric on both sides. All right, that's kind of like the goal. Make it even thinner though, right? Nice and sharp. Liquid chromatography, I mean, I guess it's kind of harder than GC, but you can get them pretty nice. But if you really zoom in, take this area, right, and really zoom in, you start seeing some tailing going on, right? It's coming up, all right, and over here it's just, so it's not quite symmetric, right? Zoom in and you start seeing this. See what I'm trying to get at? It's not quite symmetric. You get some little tailing going on, right? I guess we should write tailing. That's really what I'm trying to draw.
What does that say above the little graph?
Zoom in.
Zoom in?
So you get peak tailing. Because of, yeah, due to that OH. Not the B word though. You're on due to that stuff, right? So this is due to that, right? And why is this a problem? Why is this tailing a problem, or could be a problem? Because the whole goal of this is, right, of this, well, you can quantitate things, or you can qualitate things. But either way, don't you have to have nice resolved peaks, right? And if you have tailing, it's going to be even more difficult to resolve things, right? Look, it's tailing off, and it's going to co-resolve with something else. So you want as sharp as possible, nice sharp peaks. So you'd think that, oh, zone broadening is because things are getting fatter. Well, not if you're not doing things right? You could have other complicated things that are complicating matters and making it peak tailing, for example. So that's not really diffusion. That's just, hey, you could improve your chromatography. Okay? Does that make sense? How about this one? John, a blank stationary phase is referred to as reverse phase chromatography. Nonpolar. Yeah. Because polar was normal. Right. How about if you're going to do this C18? Use that as a stationary phase. That would be what type of chromatography? Richie, that would be what type? Would that be
Reverse phase.
reverse phase? Yeah, because it's a very organic. How about C8? Still, it's all organic, right? It's all organic stuff. Except, just realize, I think only chromatographers use this. It's the only time I've seen it. Which one's more organic? C18. Right? Well, it's kind of odd. I've never heard that type of talk. Only in chromatography do I hear that. Right? Okay, so where's the C18, the C8 stuff? It's a stationary phase that's coated on the little glass beads. Right? Okay. Benzene is injected onto a C18 column. Right? So inside these... Oh, hey, what was the name of this little guy? What was the name of the big, long guy in that drawing you just did?
Guard column, anal column.
Guard column and analytical column. Hopefully you're not abbreviating things, right? Yeah, guard column, analytical column. So the big long one is the analytical. Little short dudes are the guard columns. Okay, so you have little tiny glass beads coated with this stuff jammed in there to those columns, and we are going to shoot benzene. Okay, so we have our detectors, we have our signal versus time on all these. What would be the difference? Now you're only supposed to have one analyte, so you should only be drawing one peak here in each one of these. Emily, how would they differ? Well, I assume you're going to inject the same amount on each one, but how are they going to differ? Or would they be the same? Definitely not the same. John said they're going to differ in time. He's right. Sandy, how are you going to draw these? Times 0. So she says one is going to elute faster. Which one? C8? Why? Less carbons. Like dissolves like. Yeah. So draw the peak on the C8 so that it comes out faster than it did on the C18. Right? Try to draw it nice and pretty. All right. Like if you're going to put the C18 one here, right? The C8 one has to come out even faster, right? So you have to draw it even more inside. You can maybe label it to really express the fact. Okay, 2 minutes. Okay, then over here at 1 minute or something. I don't know, right? Okay. How could either of these peaks be made to elute even faster, Andy? Well, you got to stick with the C18 and the C8. You're right. You could change the column. That's true. But they're talking about, no, use the C18 column, use the C8 column. What could you do to make this stuff elute even faster? And I guess we're doing LC. We're doing liquid chromatography. What's that? Ooh, change the mobile phase composition. Make the mobile phase composition, Pablo, more what? More nonpolar. Make it more organic. Like dissolves like. That's one way. Make the mobile phase more organic or nonpolar, right? That sounds better probably. One more way, which I thought you were going to say, I forgot about the mobile phase composition. Adriana, what's another way? Because I was thinking this one. This is the easy one. I thought it was the easy one. We're doing LC. Just what? Well, see, that's good thing to get over, right? You add more stuff, does the retention time change? No. Put this compound in a whole different matrix. Does the retention time change? No. The flow rate, that's what I thought you were going to say. Increase the flow rate. Increase the mobile phase flow rate. Okay. Using a C18 column, a sample of gasoline was injected onto a liquid chromatograph using a mobile phase of 45% ethanol, 55% water, and a column temperature of 30 degrees Celsius. Okay. Can this chromatogram be improved? Okay, so I have to sketch it. Signal, time, and you got a bunch of stuff here. Okay, so you see the 35 minutes, you have this really late eluding peak. So Anna, assuming you're not getting paid by the hour, what could you do to fix this thing up? Oh, you get paid good money for this. What could you do? What's wrong first? Yeah, you're wasting a lot of what? A lot. Well, not only time, really.
Water and ethanol.
Oh, this stuff can go down the drain, though. So I guess it's not. I should change that to something that can't go down the drain and more expensive, right? Ethanol can, right? You're not supposed to dump ethanol down the drain, but come on, beer, everything else. Yeah, you didn't hear that here, but it's recorded. I guess lecture 6 will also be deleted. Okay, Anna, how can you fix this? Can you do?
Wouldn't you change the percentage?
Good. Your Andy's onto something. What type of run is this? Right now it is a isocratic. So we have to change the run to be a gradient, and your Andy's onto something, right? Oh, we should add. We don't have all the specs in here. We should say the flow rate is typically like 1 mil per minute or something. We have the temperature of the column. That's about it. What could we do? Your Andy's onto something. Alice, can you finish what she was talking about? You could change the temperature. You can change the temperature, but it's not going to be as effective as changing the mobile phase composition. And the only way you'd really believe me in that is if you do it. Oh, that would be okay. We could not do your Andy's idea. Do Alice's idea.
Burn.
Right? Increase the flow rate when? Increase the flow rate when? After 5 minutes. Look, according to here, there's no other peaks. So nothing's going to co-elute. You could crank up the flow rate after 5 minutes. No, I didn't think of this until she said it. Crank up flow rate after 5 minutes. So what would you crank it up to?
Whatever you want.
Yeah, whatever the thing can handle, right? Because there's nothing there. Okay. Your Andy's ideas, though, they're really the way to go, probably. Well, maybe not, man. Here, in this case,
Let's combine them.
guess you'd find out by doing the experiment. Let's do your Andy's way, Ashley. What would you do?
Just to change the percentages of ethanol and water.
You want, now realize what type of chromatography, this is my logic always has to start this way. What type of chromatography is this? Yeah, liquid, but the stationary phase. This is, so with an R, this is reverse phase chromatography. So that means this compound is the most what out of all these? He's the most nonpolar. That means if you want him to elute faster, need more nonpolar in the mobile phase. So you pretty much have to write this out. You have to say 45% ethanol, because you don't want to mess with the beginning. 45% ethanol, 55% water, until, and then you finish it. Until 5 minutes, then what? Then what? To what? Just pick a number.
65.
90% ethanol, 10% water. You really don't know. That's the whole chromatography thing. Is you gotta just try it, right? Okay, until 5 minutes, then run, all right, whatever you said. Right? You could also, it can also be set up so that by when 10 minutes is reached, it reaches 90% ethanol, 55% water. The composition could be changing the whole time.
So
There's a lot of options.
Does that mean that you wouldn't add a non-polar solvent, you just use a less polar solvent?
You're, in that flow diagram that you made, that solvent proportioning valve is sucking out more of the ethanol than it is from the water. So that the mole phase composition is now, you just increase the organic part.
Fancy one with like 4 tanks on it, expensive. Could I not throw that in there?
Well,
It's non-polar.
oh yeah. Yeah, you could use a whole, exactly. You could, yeah, just make your mobile phase more non-polar. Yep. And the only way that you can really see that is just you decrease, you recognize your polar solvent, and to see that his percent's going down, and it should work.
So which one of those are we going to increase the percent of after a while?
The ethanol.
Okay, it's more.
So then the mobile phase will be more
It's more non-
non-polar. So then this, because like dissolves like, this is the most non-polar compound in all of them. And all that thinking for me starts with realizing, oh, I'm doing reverse phase chromatography. Since I'm doing reverse phase chromatography, I need to increase the organic composition. Okay.
Put octanol in this.
Okay. Let's see. I don't know if there's much I can really say here. LC ideas. Okay, so there are some limitations to it. It sounded like, oh, LC, can you pretty much shoot anything, whatever you want, right? But coating these little glass beads kind of limits you in certain areas. But this first one, I mean, it doesn't really matter what your stationary phase is. If your mobile phase doesn't mix, yeah, you're not going to have a mess, right? So you can't use two solvents that are immiscible, right? So you can see the two layers, right? Okay.
Right where that little white line is?
Yeah. Right where the white arrow is. Right. pH less than 2 destroys the column. So these pH extremes, the chemistry of making those bonded phase glass spheres, it can't handle extremes in pH. Okay. You have to filter everything. Well, I don't really have it, but all it is we have these little whole bunch of filters that you jam onto the end of a syringe. And it's really nice because I'll have to bring it and show you. Suck the stuff up, shoot it through the filter, throw a little filter away, and it makes it really easy. It's just everything's disposable. But everything needs to be filtered really, really well because you saw the column. It's just really one big filter in itself. It could be, right? And all the little tubing connected to it, that stainless steel, everything is so narrow, low volume. You got to be careful. Extremes you wouldn't go to. So if you wanted to change your mobile phase composition, you'd never go to 100%. Extreme is 95% of anything. And the reason why is you have these big, long, very often, this is what people are working with, this type of stationary phase. And if you go to an extreme like 100%, even 95% isn't that good for it. This stuff starts curving down on itself. This thing starts curving down, and it can trap the buffer inside there. And then you can really do some damage chemically. So that's just by trapping buffer. So buffers you got to be careful with. Yeah, everyone's doing reverse phase chromatography pretty much. Pressure is the diagnostic tool in LC. Yeah, pressure's skyrocketing, something's clogged, something's messed up, happens a lot, right? Leaks would not be a good thing, right? And the pressure would be dropping in that case. Separations are more complex than liquid chromatography, right? Because there's this interaction going on between the mobile phase and your analytes, right? And that's about it. So, have a good day.